This evening I have the distinct pleasure of introducing this year's recipient of the ACS's highest honor, the Priestley Medal, a man who is credited with helping create the field of bioinorganic chemistry. Stephen J. Lippard is the Arthur Amos Noyes Professor of Chemistry at MIT. His 1994 textbook, Principles of Bioinorganic Chemistry, which he co-authored with Jeremy Berg, has served as an introduction to this subject for thousands of students. The research done in Professor Lippard's laboratory focuses on the interface between inorganic chemistry and biology. His lab discovered and named the first metallointercalculators, platinum terpyridine complexes that insert between the DNA base pairs and unwind the duplex. This research was followed by extensive studies of the covalent interactions of cisplatin and related cancer drugs with DNA and its constituents. The knowledge gained in this research has been used to design and evaluate candidates for improved platinum anti-cancer drug therapy. He recently co-founded Blend Therapeutics to translate those discoveries from the laboratory into the clinic. In addition to his research accomplishments, Professor Lippard has an equally impressive record of service to the American Chemical Society, including Associate Editor of the Journal of the American Chemical Society from 1989 to 2013. Associate Editor of Inorganic Chemistry, Chair of the ACS Division of Inorganic Chemistry and its Bioinorganic Subdivision, and member of several ACS editorial boards. His contributions go well beyond his service to the ACS. He is chair of the NIH Synthetic and Biological Chemistry A Studies Section, member of the boards of directors of International Society of Zinc Biology, and until very recently, the Chemical Heritage Foundation, and former chair of the Gordon Research Conferences on Metals and Biology and on Inorganic Chemistry. Professor Lippard has trained and mentored more than 110 PhD students and innumerable undergraduates and 150 postdocs. In fact, a fellow MIT professor says that Steve takes more undergraduates into his laboratory than any other member of the chemistry faculty. Dr. Lippard has received numerous honors for his scientific work, including the National Medal of Science, Linus Pauling Medal, Ronald Breslow Award for Achievement in Biomimetic Chemistry, and the Alfred Bader Award in Bioinorganic or Bioorganic Chemistry, to cite just a few of his awards. In addition to being a 52-year member and a fellow of the American Chemical Society, Dr. Lippard has been elected to the National Academy of Sciences, the National Institute of Medicine, the German National Academy of Sciences, Leopoldina. He is also a member of the Scientific Advisory Board for the University of Basel in Switzerland, and a fellow of both the American Academy of Arts and Sciences and the American Association of Advancement for Science. He has more than 840 peer-reviewed scientific publications to his credit. He also has 30 patents issued, pending, or filed. Steve Lippard is a native of Pittsburgh. He earned his undergraduate degree in chemistry from Pennsylvania's Haverford College in 1962 and his doctorate in inorganic chemistry from MIT in 1965. The following year, he joined the faculty of Columbia University, where he remained for 16 and a half years until his return to MIT in 1983. He served as a head of MIT's chemistry department from 1995 until 2005. Beyond his scientific pursuits, Steve enjoys jogging, playing the harpsichord, and is an enthusiastic fan of the world champion Boston Red Sox. He and his late wife, Judy, have two sons, Josh and Alex, and a daughter-in-law, Sandra, and twin granddaughters, Annie and Lucy. He and Judy were housemasters of McGregor House, a prominent MIT undergraduate dormitory, from 1991 until 1995. Ladies and gentlemen, for his many years of distinguished service, distinguished research, service to chemistry, it is my honor to present the 2014 Priestley Medal to Professor Stephen J. Lippard.
Well, thank you so much. I'd like to begin by acknowledging the presence of my sons, Josh and Alex. I appreciate their coming and supporting me on this wonderful occasion. I thought I'd just start with a little story. It's very short, but it took place in ancient Rome. And it was in the Colosseum, and you may remember that the emperor would call out the gladiators, and the lions would come from all around. And there's gladiators out there in the middle, and the lions circle around him, ready to pounce, and he calls the head lion up, and he goes over to him, lifts up his ear, and whispers a few words. And the lion then cocks his head, walks around, talks to all his fellow lions, and they disappear to the shadows of the Colosseum. And the audience goes wild, raise the thumbs up. They definitely want to let him go, and the emperor knows he has to let him go. He calls him over, and he says, "I will let you go, but you just have to tell me, what is it that you said to that lion?" He said, "I simply said, after dinner, there will be speeches." I'm truly honored to receive the 2014 Priestley Medal. This award is attributed to the talented students, both graduate and undergraduates, as well as postdoctoral associates who have trained with me over nearly 50 years. I'm proud of these individuals for their courage in agreeing to venture onto new snowfields to place the first footprints, for their relentless pursuit of the truth, for their creative ideas and clever experiments that brought insight where previously there was often confusion. Of equal importance are the many collaborators who have greatly facilitated our ability to make progress in areas beyond our knowledge base. If professor stands for professional student, as I have long believed that it does, these individuals have been my teachers. I thank them, the ACS Board of Directors who award this medal, and those who entered and supported my nomination. While contemplating the message I wish to convey here, I chanced to read in Nature an obituary by Alan Bernstein and Janet Rossant describing the biochemist Tony Pawson. In receiving an award in 1998, Pawson spoke of several facets of his life as an academic scientist that mirrored some of the themes that I had already chosen for my Priestley address. Three of them, the joy of discovery, the privilege of working with talented young people, and the importance of family, together with the opportunity to serve, are told here in the context of my own experiences, which I hope may be a source of inspiration. I consider it good fortune to be surrounded by bright young people, students and postdocs with energy, enthusiasm, and ingenuity. As a professor or professional student in the environments of Columbia University and MIT, I learned many things from my graduate students and postdocs. I learned that the amount of time a person spends in the laboratory is not a good measure of what he or she will accomplish. One of my first graduate students, Karen Jeanette, commuted 90 minutes each way every day, yet managed to get more research done than many of her lab mates. I learned to recognize and nourish the qualities that make for a good chemistry graduate student, such as commitment and self-reliance. Some of my group members, like captains of sports teams, and some were noted for their dedication, leadership, positive thinking, unselfish nature, and ability to foster harmony among coworkers. Some, like people raised on farms, and some were self-reliant, perseverant, and observant. I learned not to be surprised by the decisions of my group members. My graduate student, Wes Sundquist, nearing the end of his fourth and final year, made a pivotal discovery. He placed an NMR tube containing a deep blue solution of a platinum complex in the refrigerator at the end of the day. When he returned the next morning and removed the sample, the solution had turned deep orange. Further studies confirmed unparalleled thermochromic behavior, and he begged me to allow him to stay another year to continue the work. Given his talents, I could hardly say no, and today Wes is a famous biochemist. I learned in time that not all PhD students pursue a career in chemistry. Law, medicine, elementary and high school teaching, management, consulting, and a host of other opportunities are there for chemists with advanced degrees. What matters most is happiness and fulfillment in the job. It should be fun to walk out of the door each morning on the way to work. I encourage my students to seek that happiness and to pay little attention to conventional wisdom about a particular occupation. I teach them that the most important decisions in life are made not in the head, but in the gut. So how does one help students choose research projects? When graduate students or postdocs begin their research, I ask them to consider the circle of chemistry and to draw a diameter. One semicircle represents small molecules and the other macromolecules. I then ask for a second diameter perpendicular to the first, defining two more semicircles, making things and measuring things. I then ask which quadrant best defines your talents and interests. This conversation facilitates further discussion and ultimately helps identify the topic that is likely to be a focus of their thesis research. Academic chemistry is the incubator of innovation as ideas become reality. Graduate students, unfettered by experience marked with failures, are usually willing to try anything, thank goodness. Yet when I ask first-year graduate students what emotion best defines your time thus far in graduate school, for many it is fear. Fear of falling short of their expectations, of projects that lead to dead ends, of their inability to find their way past experimental obstacles. It reassures them to know that fear is common. These students are in transition between a course taker, problem set solver, and a pioneer facing an endless frontier of experimental choices. It can be scary not to know where to go next without the benefit of prior knowledge. Deciding when to stop pursuing an objective is one of the most difficult decisions in science. I characterize the transition from undergraduate course taker to graduate student research achiever as passing through the eye of a needle. Experiments begin to produce meaningful results, self-confidence is restored, and the road to the PhD is established. Postdocs bring maturity to the laboratory and skills from their prior training that significantly enrich the environment. Their first group meeting assignment is to present a seminar on their PhD thesis research. It provides a comfort zone for them in their new surroundings, while educating other group members about the methodologies they have mastered and how they were taught to think about chemistry. Undergraduate students, called UROPs at MIT, are a special breed. Because of the many demands placed on their time, they tend to focus intensely when doing their research. One of my former graduate students, Matt Szynski, mentored as many as 4 UROPs at one team, running a mini-group inside the larger group and making remarkable progress in his research program. He is now a faculty member at Pomona College, where this experience has served him well. Faculty members in chemistry departments are brothers and sisters in education, research, and service. They need to support each other, for it is not easy to make the transitions from student to full professor. Departments that foster collegiality flourish. At MIT, we have had monthly faculty dinners. Preceded by a brief social hour, each of these events was highlighted by a research presentation from one of the faculty, presented as the dessert was served. Hearing from the younger faculty was especially valuable, for it often engendered helpful suggestions from senior colleagues and sometimes collaborations. Not everyone loves classroom teaching, but I do. Teaching offers the opportunity to bring perspective about the subject to the students. by framing recent advances in the context of existing knowledge. For the faculty, teaching is a great way to remaster the basics, and it often inspires research ideas. For the students, it can be an amazing experience to have a faculty member take a textbook course and place it in the context of contemporary research. As an undergraduate at Haverford College, I was a pre-med major until Colin McKay and other faculty, including visitors, exposed me to the beauty of chemistry. I especially love teaching freshmen, where it is both possible and desirable to perform many demonstrations to illustrate and enliven the lectures. The books by Bassam Shakashiri, who's in the audience this evening, provide guidance by performing classroom demonstrations in a safe, dynamic, and instructive manner. Teaching advanced courses has the advantage of smaller class sizes. As a strong believer in the Socratic method of teaching, I value the opportunity to address questions in real time. A well-planned lecture budgets time for such discussion, where one can sharpen critical skills by encouraging students to question prevailing paradigms. In advising students about courses to take, I tell them that lectures are as much about professors as they are about the specific subject matter. What is said between the lines imparts wisdom beyond that of the printed text. How does one choose a research project? My personal preference is to address a specific problem rather than develop methodology. But exactly what is worth studying? The inspiration can come from many sources. Senior scientists offer a special opportunity for young faculty starting out. An example is a conversation that I had with the late Bill Phillips of DuPont when I was joining the Columbia University Chemistry Department as an assistant professor. Bill recounted a strategy being pursued by Michael Beer of Johns Hopkins University to sequence the human genome by attaching heavy atoms at base-specific positions and then reading those sites through an electron microscope like beads on a string. I envisioned a tactical approach to achieve the requisite specific labeling of the nucleotides. In collaboration with Fritz Eckstein of the University of Göttingen in Germany, we incorporated sulfur atoms into the sugar phosphate backbone of the DNA or RNA to direct the binding of mercury or platinum complexes selectively to these positions. The chemistry worked well, as expected from the hard-soft acid-base theory, but despite much effort, it was not possible to read the positions of the heavy atom beads on the string of DNA nucleotides with sufficient resolution in the scanning transmission electron microscope. During the course of these studies, however, Karen Jeanette, graduate student of mine, in a proof-of-concept experiment, examined the binding of platinum complexes containing planar fused ring aromatic heterocyclic ligands to a transfer RNA molecule having a naturally occurring 4-thiou base. This preliminary work led to an exciting discovery. Seemingly sterically encumbered platinum complexes bound better to the sulfur atom in the tRNA than did less hindered mercury salts. We proposed that the platinum complexes were intercalating between the stacked base pairs of the double-stranded RNA. Soon thereafter, we proved with newly discovered superhelical DNA that this type of binding, which we termed metallointercalation, was a general phenomenon. Bill Bauer of Stony Brook, SUNY, was a valued collaborator in this work. Next, we examined the DNA sample containing the intercalated platinum complex by a method known as fiber X-ray diffraction, in collaboration with Peter Bond, a postdoc, working in Bob Langridge's lab at Princeton University. Peter had trained with the Nobel Prize winner Maurice Wilkins at King's College London and was an expert in this method. Late on a warm summer evening on the beautiful Princeton campus in 1975, Peter, Karen, and I eagerly awaited the development of X-ray films portraying the diffraction pattern. There, superimposed on the famous cross pattern of double-stranded Watson-Crick DNA, were 10.2 angstrom meridional reflections arising from the regular spacing of heavy platinum atoms stacked according to the so-called neighbor exclusion rule. This rule dictates that the presence of an intercalator between DNA base pairs excludes the next nearest neighboring interbase pair sites on either side. Thus, the platinum-platinum distance would be 3 times the thickness of an aromatic ring, or 10.2 angstroms. It is impossible to exaggerate the joy of this discovery. It had been predicted from indirect methods that intercalators would be subjected to the neighbor exclusion binding to DNA, but no one had visual proof of such. Moreover, it set for the course for decades of future research in my group centered on the interactions of transition metal complexes with DNA. At about the same time, the anti-cancer activity of cis-diamine dichloropplatinum, this little 11-atom compound known as cisplatin subsequently, was discovered and immediately drew my attention. What could be more important a project than to understand the mechanism of what was to become a leading, if not the leading, anti-cancer drug? Because work by Barnett Rosenberg, who discovered the anti-cancer properties of cisplatin, and others pointed to DNA as the likely target of the compound, I was eager to apply the research experience gained in studies of metallointercalation to this new project. Our investigation of platinum anti-cancer agents produced many rewarding discoveries and much satisfaction to research group members involved in the pursuit. Some of the high points include the following: structural characterization of a crystalline platinum blue by Jackie Barton, elucidation of the major adduct and intrastrand deoxy-GPG crosslink formed by cisplatin on single-stranded DNA by Suzanne Sherman and double-stranded DNA by Tricia Takahara. Discovery by Sue Brune, Peter Pill, and Jeff Toney, as well as Brian Donahue and collaborator John Essigman's lab at MIT, that high mobility group proteins bind the platinated DNA crosslink, and determination of the X-ray structure of one such protein platinated DNA adduct by Uta Maria Ondorf. We also deduced many aspects of the molecular mechanism of cisplatin, which ultimately led to the realization that monofunctional platinum complexes, which form only one bond to the DNA basis, could also display potent anti-cancer activity. Unlike the intrastrand crosslinks formed by cisplatin, monofunctional compounds do not bend DNA, which retains the canonical Watson-Crick structure upon platination, as shown by Ryan Todd. Monofunctional complexes provide an untapped source of novel anti-cancer drug candidates, and they are not restricted to platinum. They provide the potential for new metal-based cancer treatments, and as you heard, I have been involved in the co-founding of Blend Therapeutics with the ultimate goal of curing people of cancer. As I've said before, I would really like to cure at least one person of cancer before leaving the planet. Many other projects produced joyful discoveries that are briefly recounted here. Included our reductive coupling of adjacent isonitrile or carbonyl ligands in second and third row early transition metal complexes to form carbon-carbon bonds, work by Chu Lam, the most interesting of which to me was a coordinated dihydroxyacetylene generated from carbon monoxide by Ray Verdes. The first model of a carboxylate-bridged diiron protein active site, that of hemerythrin, by Bill Armstrong. Determination of the structure of the hydroxylase component of soluble methane monooxygenase, Amy Rosenzweig, and a so-called molecular ferric wheel produced in the pursuit of a model of the ferritin core structure by Kingsley Taft that defined wheels as a branch of self-assembled polymetallic chemistry. Work to obtain fluorescent probes to investigate the roles of inorganic species, specifically zinc and nitric oxide, at the interface of inorganic chemistry and neuroscience, led to constructs that can serve as signaling agents for neurotransmitters. Included are sensors for mobile zinc, work of Sean Burdett, Liz Nolan, and Chris Chang, nitric oxide, Mihi Lim, nitroxyl, Joel Rosenthal, as well as the pathological metal ion mercury, Liz Nolan. Studies in collaboration with Jim McNamara at Duke University used a very rapid zinc chelator, ZX1, invented by Xiaolan Zhang, which enabled us to prove a role for mobile zinc at the mossy fiber CA3 synapse in the brain's hippocampus, the center of learning and memory, that is critical to control of the efficiency of communication between these nerve cells. We use the term metalloneurochemistry to describe this line of investigation. In many of the foregoing examples, the motivation was either to understand metal-based chemistry that underlies important functions in bioinorganic chemistry, or to apply coordination chemistry to probe biological signaling events and to diagnose or treat disease. But there are many unmet challenges in fundamental chemistry for consideration in choosing research projects. More than a decade ago, I wrote a list of these grand challenges and was published in Chemical and Engineering News in 2000. And I've discussed them with physicists, biologists, and other scientists as examples of important goals in pure chemistry. Significant progress has been made in addressing these challenges. Some of my favorites are the following: to create self-replicating molecules and self-correcting chemical reactions, to devise reagents and pathways for activating chemical bonds viewed to be inert, to modify chemically a portion of a molecule having many functional groups without protection-deprotection steps, and to refine and utilize the chemistry of polyatomic radicals. Many in our field view chemistry as the central science. I am not one who favors this description, for it could be interpreted to mean that we are a service discipline, one that touches on many surrounding areas: biology, chemical engineering, solid-state physics, material science, neuroscience, medicine, without recognition that we have a plethora of important grand challenges. My list of goals is neither complete nor necessarily even a good one. I encourage others to improve and expand it. Synthesis is the heart of chemistry. It is the singular pursuit in our science that is unlikely to be seriously addressed by colleagues in neighboring disciplines who often co-opt our ideas and language, witness synthetic biology, with little likelihood of supplanting what we chemists recognize as synthesis. Theoretical, physical, analytical, and other chemists for whom synthesis may not be a prime objective nonetheless serve the art and science of making things by providing insights into the nature of bond-making, bond-breaking reactions, steps that ultimately underlie all chemical synthesis. Circling back to my own research, the synthesis of new molecules and the physical understanding of biochemical transformations that generate essential biomolecules are intimately involved in many of the projects that my lab has undertaken. The Priestley Medal recognizes distinguished services to chemistry, which thus far have been exemplified by some of my research contributions and by the education and mentoring of students. But there are many other opportunities to serve that can enrich one's personal life. I am grateful for the invitations to serve the inorganic community as editor of Progress in Inorganic Chemistry, and the bioinorganic chemistry community as associate editor of Inorganic Chemistry, and then the Journal of the American Chemical Society. I thank Bruce Armbruster and University Science Books for encouraging me, in collaboration with Jeremy Berg, to write our textbook, Principles of Bioinorganic Chemistry. The opportunity to serve on 2 National Institutes of Health study sections allowed me to give back to the community that enriched my professional life by supporting my research activities, and fortunately continues to do so. That service has had an unexpected benefit in sharpening my skills in writing grant applications. It reinforced my conviction that a major strength of science in the United States is the need to pass critical peer review in order to continue one's research. Seniority is no guarantee of continued funding. A rather unusual opportunity to serve came in 1991 when I was invited to become housemaster of McGregor House at MIT, a coeducational undergraduate dormitory housing approximately 350 students. During the first year, I volunteered to teach a year-long course on Baroque musical instruments and performance, which met from 9 p.m. to midnight on Mondays and was restricted to McGregor residents. I quickly learned that the students really begin to become alive around 9 p.m. at night. I play the harpsichord and I enjoy Baroque music, so sharing this pleasure with the undergraduates was of interest. Moreover, it provided an opportunity to enrich the lives of young people in a manner similar to what I had enjoyed as an undergraduate at Haverford. The course, which required approval from the music department, was given pass-fail and could not be counted toward the major. Little did I know what I was taking on. Not being trained in music education, running this course was one of the harder things that I've ever done. The learning curve required to prepare and teach the material was steep, but with help from faculty at nearby Longy School of Music in Cambridge, who came and demonstrated their Baroque instruments to the students, and thanks to the talents of those enrolled, we made it work. We gave 2 public concerts which were well attended and quite enjoyable. One of the students in my course, a pianist and composer with enormous talent, named Jose Elizondo, was quite taken with the harpsichord that I had raised funds to rent for the academic year. It was housed in the McGregor House music room where the course met. In addition to science and engineering, Jose loved and wanted a career in music. But his father, who expected Jose to join the family's potato farming business, was initially reluctant to support even what he saw as his son's more practical electrical engineering degree. Music was out of the question as a career option. But with much effort and dedication, and thanks to opportunities MIT provided, including my seminar, Jose pursued both degrees. When the San Jose Symphony Orchestra premiered his first symphonic suite, he received a standing ovation by a crowd of 25,000 people. At age 24, he was the youngest composer to have his work performed by that orchestra. Of great satisfaction to me was his informing me that his father attended that premiere and finally became reconciled with his choice of music as a career. It is not easy having an academic scientist as a life partner. I have accordingly counseled my group members to choose wisely. That wasn't meant to be funny. That person must understand the dedication required for success and fulfillment. Chemistry experiments set up on Friday afternoon may often not wait until Monday morning to be worked up and extended. Some experiments require attention late into the evening, or even a return to the laboratory long after normal business hours. Unlike many professions, experimental chemistry cannot be done from the comfort of one's home via the internet. I have witnessed a number of relationships, including marriage, dissolve because the partner of a chemist did not understand what is required to support them in their choice of career. My personal situation has been extraordinary, as many can attest, who had the good fortune to know my late wife, Judy. We met at an MIT mixer, my first and only one. I only needed one. In September of 1963, when she was an undergraduate at Simmons College and I was a graduate student at the Institute. We were engaged in December, married the following August. She was 21 and I 23. Although her talents for painting, sculpture, and other forms of art were substantial, she chose instead to devote herself to our children and to our family, supporting me in my career. Many, if not all, who know me well credit Judy for my success as a scientist. It is true. She was then, and to the end, my greatest fan. Only much later, when I became associate editor of Inorganic Chemistry and then the Journal of the American Chemical Society, did Judy begin a career as a journal editorial assistant. This was a post she finally relinquished when we had to abandon our work on JACS in August of last year. Judy worked from her bed in Massachusetts General Hospital until her cancer became too much for us to continue. Judy was very brave and wise as she faced her death, counseling family members to make their days count and to help, respect, and love each other going forward. Her major regret was not being able to see our beautiful twin granddaughters, now 4 years of age, graduate high school. I took her everywhere, nearly everywhere I traveled, and the communities of inorganic and bioinorganic chemists were counted among her good friends. The outpouring of letters and emails that came to me after her death on September 9th of last year is extraordinary. I conclude my remarks by honoring Judy. The love that we had for each other endures in my heart and mind. I dedicate this Priestley lecture to her memory. Thank you.
I hereby declare this 2014 meeting of the ACS to be over.